All right, let's get into it. Today, we're going to crack a code. And I'm not talking about some secret message. I'm talking about the code that lets computers solve puzzles that feel like they should be impossible without, a human brain.
Just look at this. A good old-fashioned Sudoku. For you and me, solving this is all about intuition, right? It's that little spark, that aha moment when you finally see where the next number goes. It feels human.
And that's the big question, isn't it? How on earth do you write code for intuition? How do you program that aha moment? It seems like you can't. But here's the secret. It's not about teaching the computer to think like us. It's about giving it a completely different, and honestly, a much more powerful way to see the problem.
To really get how this works, we have to stop looking at the puzzle as a whole. Instead, we need to see it for what it really is, just a collection of really simple, logical pieces.
See, a computer doesn't see a fun little number game. It sees a problem that it can take apart piece by piece. The real trick here is turning this fuzzy, intuitive puzzle into a set of cold, hard, logical facts.
So, let's do it. Let's do that deconstruction. We're going to translate Sudoku into a language that a computer can actually understand. And believe it or not, this language only has 3 key words.
First up, we have variables. That's just a fancy word for the unknowns. In a Sudoku puzzle, every single empty square, all 81 of them, is a variable. It's a question waiting for an answer.
Next, we've got domains. Every variable, every empty square, has a limited set of options. For any given cell in Sudoku, its domain is just the numbers 1 through 9. That's its entire universe of possible choices. Simple as that.
And finally, maybe the most important word of all, constraints. These are just the rules, the things you absolutely cannot do. For Sudoku, it's pretty straightforward. No repeating numbers in any row, column, or 3x3 box. And these constraints are what tie everything together. They're what make it a solvable puzzle.
Okay, so we've got our variables, our domains, and our constraints. What we've just done here is way more than just a neat trick for solving Sudoku. We've actually stumbled onto a universal framework for solving all sorts of problems.
Yeah, this whole method of breaking down a problem into these 3 parts has a name. It's called a constraint satisfaction problem, or a CSP. And what's so cool about it is that it's a super general way to represent a huge class of problems that, on the surface, look totally different from each other. So here it is, the formal definition. Any problem that you can define with a set of variables, a domain of possible values for each of those variables, and a set of rules, or constraints, well, that's a CSP. You already get it. This is just the official name for it.
Now, to really see how universal this is, let's look at something totally different. This is the n-queens problem. The challenge is to place 8 queens on a chessboard so that none of them can attack each other. Looks nothing like Sudoku, right?
Well, watch this. We can map it to the exact same framework. The variables? Let's just say 1 for each queen. The domain for each queen, it's just which column it can be in, from 1 to 8. And the constraints? Simple. No 2 queens can be in the same column or on the same diagonal. It's the same structure, variables, domains, constraints. Okay, so we have this universal language to describe these puzzles. But that doesn't tell us how the computer actually finds the solution. That's where this really elegant search strategy called backtracking comes in.
The big idea here is that we don't try to solve the whole thing at once. Instead, we build up to a solution one piece at a time, making one decision, then the next, searching through all the possible options in a really organized way.
And that organized way is called backtracking. Think of it like you're exploring a maze. You pick a path and you go down it. If you hit a dead end, what do? You backtrack to the last place you made a choice and you try a different path. It's the same thing here. Pick an empty square. Try putting a number in. Does it break a rule? Yes? Okay, undo that, try the next number. If it doesn't break a rule, awesome. Move on to the next empty square. This whole process creates what you see on the left, a search tree. Every single branch is a choice the algorithm makes. And on the right, you can see what this actually looks like for the n-queens problem. The computer is just exploring this tree of possibilities, placing a queen, checking for a problem, and if it finds one, it just backtracks until it finds a path that leads all the way to a complete solution.
Now, this backtracking method, it's really powerful. But it can also be, let's say, a little bit dumb. It can wander down a whole lot of wrong paths before it realizes it made a mistake way back. So, the question is, can we make it smarter?
Take a look at this Sudoku board.
It's pretty obvious to us, to a human, that the highlighted red square is impossible, right? There are no legal numbers left for it to be.
But our basic backtracking algorithm, it won't notice that. It'll just keep on filling in other squares, doing potentially thousands of pointless calculations, before it finally gets to that red square and goes, oh, wait, I have no options. It's a massive waste of time.
The solution, the smarter part, is something called constraint propagation. Basically, it's the art of looking ahead. Every time the algorithm makes one choice, it immediately propagates the consequences of that choice across the board. It looks at all the other squares and eliminates options that are no longer possible. This lets it spot those dead ends immediately, which means it can just chop off huge dead-end branches from the search tree and find the solution way, way faster.
And this is where it all comes together. This entire process, defining variables, domains and constraints, and then using a smart search to find an answer, this is not just for games, not by a long shot.
This exact same logic is the engine behind some of the most complex systems that run our world. We're talking airline flight scheduling, factory production lines, creating a timetable for an entire university, even designing the physical layout of a computer chip or planning delivery routes. They're all just really, really big constraint satisfaction problems.
Which kind of leaves us with one final thought. Once you learn to see the world in terms of variables, domains, and constraints, you start to see these kinds of puzzles everywhere. So it makes you wonder, how many challenges in our own lives are just waiting for us to figure out the right rules to solve them?